B and C are fixed, it says, while A moves on the arc. And O is the circumcenter. I is the end circle. And it's tangent at D. And then we draw the excenter. So let's see, let's make some room for it. Let me just make a little room here. There we go. That's a little better. Okay. So we want to draw the AX center. And I mentioned doing it like this, so this is my favorite way to do it. There's the X center. Let's draw the X circle. All right. Oops. Hide a bunch of stuff. Okay. So IA is the X center. And IAD cuts OI at L. Interesting. E is on the end circle such that DE is parallel to AI. So let's draw this. Okay. And LE cuts AI at F. So draw this whole line and okay. So this is F up here. Let me check the chat in just a second. Call this G. Shrink this. Hide this. hide this. Hide, and then do that. Okay. LE cuts AI F, and we want to show AF equals AI. Yeah, I think we did solve part A one time. It looks kind of familiar. There was another similar problem though. So I saw another kind of riddle, and I wonder if it was a different one. So, what was it? Maybe it was a middle riddle. Not this. Don't think it was that. Okay, but you think we might have solved part A before?
Yeah.
I'm too far back.
It was a long time ago.
Okay. Do you want to assume part A and try to prove part B, or
Let's do A again. I mean,
let's do A again? Okay.
from what I see now, I mean, I don't exactly remember how I did it, but the first thing which comes to mind is just to project AIF infinity onto OI,
Okay.
and then project through D onto AI again. And this simplifies the problem a lot.
So project AIF through E onto OI?
Yeah.
Okay. So we get IL this point. And then infinity. So, oh, that's already parallel. So, okay, let's see how I can draw this. So this point right here. Doesn't want to draw it. It's stubborn. But that's just the midpoint of EB, so. Okay, so HLJI we want to show is
And then you project the same cross ratio through D onto AI.
through D onto AI. Okay. So I stays where it is, and then L goes to IA. That goes to infinity. Okay, so HD. We want to show HD passes through the midpoint of the arc. Okay, so we want to show HD and this point M are collinear.
So we basically want to show that MD, AE, and OI intersect at one point.
MD, AE, and OI.
Yeah.
Interesting. But is that kind of, well, okay.
And that looks kind of well known.
MD, AE, and OI. So E is just, because DE is parallel, DE is parallel to AI, right? Okay, so MD, AE, and OI.
So maybe we want to show that AI or IM is equal to EJ or JD.
Okay. So yeah, AI over IM. Well, AI over IA, we know is like the ratios of the N radius and the X radius, but let's see, EJ over JD. Wonder if anything else lies on this circle. Does J lie on that circle? Oh, none of the points have to lie on it. Okay. Yeah, I guess I really should rename some stuff because part B uses different letters, so I'll do that. Just call this K, and this instead of J, I'll call it something else. Q. Key. So DE, how did we define that? DE is parallel to AI. So if we draw DE parallel to AI, and we want to show AE, KD, and OI concur. You want to show AI over IK is EP over PD. That's one way. So OI is perpendicular to the radical axis of those two circles, obviously. I feel like there was a lot with this line OI in I3435's book. This I don't know if this helps much, but like it's well known. So IAJ is parallel to AD. Pretty sure that's true at least. Yeah. Be right back, guys. Sorry. All right. KDOI and AE. maybe we could like use the Sarg's theorem or something. So EID is isosceles. AOK is also isosceles. Yeah, so we have two isosceles triangles. Oh wait, let's think about this. Is this just a homothency? Because K is the bottommost point of this circle, and D is the bottommost point of this one. We just have to show angle EID equals angle AOK, right? Wait, now I think this might be trivial. They're both isosceles triangles and all the sides are mutually parallel. Right? So it's obvious that OI, KD, and AE concur, right? Right?
Yeah, looks good.
Okay.
But just could you repeat how you proved that? Like H is then the center of homothency, which takes in circle to X circle.
Yeah. Or yeah, takes triangle EID to triangle AOK because triangles EID and AOK are both isosceles, and all their sides are mutually parallel, right?
Yeah. Okay. Yeah.
So that proves it. All right. So
Yeah, that's true. So HD and K are collinear.
yeah. So that solves part A. I'm glad I figured out something in this session. Okay. So all right. AOK are isosceles. Sides are mutually parallel. So therefore they're homothetic. Homothetic. So AEOI and BK concur at a point H. And then once we know that, we project. Okay, so K was the midpoint of IIA. So projecting through D, first we project through D, then we project through E. So IK, IA infinity, or IA infinity. That looks a little weird. I'll say AI infinity. And then we project through D onto OI. Then we get ILHP is -1. and then projecting through E. Onto AI. Then we have IF. IF. IFA infinity is -1. And that means that AF equals AI. All right. Check the chat. Homophily can also solve it. Okay. Oh, the original solution is different. Interesting. Now, part B. Do you want to try part B or try another problem? Let's see. Oh, what were you going to say?
Let's do part B.
Okay. Let M lie on the circle J through IA, B, and C. So obviously center K. Oh, so I guess well, what they called K, we call, okay. So IAM is parallel to AB. Okay, so basically that passes through the midpoint of BC. So that's the well-known lemma that I just said. So this is M. And I didn't even have to change the name. Isn't that nice? And II is a diameter. So that makes things easy. MD cuts J again at N. And we want to show the midpoint T of MN lies on a fixed circle. So that's kind of interesting. So basically as A moves, that midpoint lies on a fixed circle. Okay. So yeah, I wish there was a way to like fix B and or fix the circle. But so this is perpendicular, that's clear. So saying that T lies on a fixed circle, let's think about that. So as A moves around, because it's saying A moves on the arc BC, I is going to move, B and C are going to stay in the same place, K is going to stay in the same place. So I is going to basically move around this circle right here. Because B, K, and C stay in the same place. M, so I and IA are going to move around this same circle, kind of rotate with each other. And J is fixed too, right? Because J is the midpoint of BC. So I and IA are going to rotate around the circle. IA is always going to meet J at M. And
it suffices to prove that intersection of DM and KJ is fixed.
Really interesting. Okay.
Then you will have that T lies on the circle with diameter K and that intersection point.
Okay.
Since KT is perpendicular to MN.
Okay. Yeah, and this line is always the same. So basically, and IA are just rotating, and M is just where IAJ intersects the circle. So okay, so yeah, D and G are like the feet of the perpendiculars here. Yeah, we can hide a lot of the diagram. Like we don't even need. All we really need is BC, IA, D, and J, and M. So, and also IMDJ is cyclic. So that might help. But yeah, I think it might help to hide like a whole bunch of pieces of the diagram. All you really need is, whoops. Yeah, we don't need point A, that can go away. We don't really need the end circle. Yeah, we don't need hardly anything here anymore. We want to keep M, but we don't need H. Let's see what that looks like so far. Whoops. Let me hide them one by one. We don't really need the X circle either. I want to show I just don't want to show. Don't need that. So IIA is a diameter. So we just want to show that as we rotate IIA, so we rotate point I, and point IA also rotates. So B, K, C, J are all fixed.
We don't even need IA.
We don't even need IA. Well, I was thinking,
IMJ is just 90 degrees. And this means that M is actually just the Humpty point of IBC.
Okay.
So we basically get rid of everything.
We get rid of everything. I like it. So M is the Humpty point of IBC.
And we want to show that dm passes through a fixed point on that perpendicular bisector of BC.
We don't even really need n, right? I mean,
Yeah.
this is funny. It's hiding everything. Yeah, so we want to show wherever we move I, dm intersects this at a fixed point. Thinking if we can project somehow.
Now maybe we invert at J with radius GB. And
JB.
like JB, yeah, and complete the orthocentric system.
Okay.
So basically drawing the orthocenter of BIC.
All right. Oh, there is no orthocenters. R. So RM and J are collinear. So RID.
R is the inversion of M.
Okay. So we're inverting. So R is the inverse of M.
Yeah.
So yeah, JM times JR is JB squared. So let's see where Q inverts to. Okay, so it inverts to that point. We want to prove that, but that's what it inverts to. And if we prove that, would that solve the problem? Because is point S fixed?
We want to show that S is fixed.
Okay. So that's like where the perpendicular bisector of BC meets, which is fixed, meets the perpendicular from C to IB. But that almost seems like it's not fixed because I can move around, right? And then as I moves around, CR, the segment moves around.
That's not true. S is just inversion of Q. And S should be, if you invert D to D prime, then S lies on circle J, D prime R.
Okay.
S is not on line segment RC.
Oh, S is, well, okay, S is not on RC. That's where I got confused. Okay. So the inversion, like this point. Oh, okay. Yeah, I got tricked. All right. So if S is the inversion, so you were saying S lies on what?
That's just from inversion. If you invert D to D prime, then in this case Q prime, since you named it to Q prime, then R Q prime J D prime is cyclic. That's just basic inversion.
Okay. So from there, we want to show Q prime is fixed. So we want to show the intersection of that circle is fixed. That's kind of the same as saying the power of K with respect to that circle is fixed. Is I the orthocenter? So are DI and M collinear? Yeah. So I is the orthocenter of D prime RJ. Yeah, IMBC is cyclic. Let me think about this. So M is the Humpty point. So I'm kind of just trying to show that like the tangent of this angle is QJ over DJ. So if I could show that the tangent of this angle times DJ is constant, that would solve it. And the tangent of
That's exactly what I was thinking also.
Okay. The tangent of this angle is the tangent of MIC. And MDJ is MJD, right? So I think, because this is a right triangle. Well, no, that's not true. So MIC is like RIC minus RIM. And maybe we could get it from there. So RIC is 180 minus DIC. And RIM is like RJD. Yeah, so let's see. I'm going to write this out, but it might just reduce to a batch. There's probably a better way, but just equal to this is dr over dj. Tan A plus tan B is CD over ID. dr IR plus IB. Yeah, so Q prime is kind of a weird point. Yeah, I agree. Okay, so this is a median. And Q prime I don't think lies on this. No. I feel like I'm making this harder than it might need to be. So angle MIC is actually angle ICD plus angle ID prime D, right? So we want to show that the tangent of the sum of those is times DJ is constant. But so the tan of this plus the tan of this, So that's like ID over DD prime plus ID over CD all over 1 minus ID squared over DD prime times CD. Tan A plus tan B over 1 minus tan A tan B. Oh no, because we need MIJ. I'm looking at MIC. We could do this something similar with that. So, okay, I think I'm getting somewhere with this. So it would just be JD instead of CD. So we can rewrite this ID times JD, ID times D prime J over DD prime times JD minus ID squared. Okay. And this is okay. I think I'm getting stuff to simplify. This is RD times ID. So we have D prime J over RD over RI. And then times DJ. Okay, so here's kind of how I'm thinking about it. I think it reduces to a bash. So I'm going to hide Q prime. I'm going to hide the circle and a bunch of stuff. And usually I don't like a bash, but oh well. So basically QJ is equal to DJ tan QDJ. Which is equal to DJ tan MDJ, which is DJ tan MIJ. I do want to leave point D prime for a sec. Oh, did I delete that? Let me do this. I'm going to copy this and then undo a little bit. So I'm going to hide that, and I'm going to hide the circle, but I'm going to leave that. Okay, so now I'm going to paste what I just had. And MIJ, which is equal to DJ times tan of IJD prime plus ID prime J. And this is equal to DJ times, so this would be ID over DJ. So I'm using the formula for tangent. So ID over DJ plus ID over DD prime. Actually, I could do it like this. Over 1 minus id squared over dj times dd prime. Whoops. Let's get rid of the log tech for the moment. I could do serif, just okay. And then if you multiply everything by dj times dd prime, you get this is going to be multiply numerator and denominator by dj times dd prime. So it's going to be dj.
So to tell you, since you just starting full bash, I solved it without a bash.
Okay, yeah, that's fine. Let's do it without the bash.
You don't have to delete it, just leave it there.
Okay.
Okay. In fact, the inversion idea actually works.
Okay.
I just needed to observe one thing for it to work.
Okay.
So we invert at j with that radius jb, and this circle rj d prime is actually as it is right now. It isn't very pretty. However, if we intersect that circle with rbc, we will get that intersection point lies on rd.
Okay.
And that is not too hard to prove. You can, for example, use the that since d prime d bc is harmonic, then you have db times dc is dj times dd prime, and you can use powerful point then to finish it. So basically, we will have that rs jq prime is an isosceles trapezoid.
Okay.
And observe also that I and S are just reflections about BC. So JI is JS, and also since we have an isosceles trapezoid, then RQ prime is equal to JS. So we have that RQ prime is JI, which means that RI JQ prime is a parallelogram. And that basically solves that JQ prime, that length is constant, since there is this problem that RI is actually constant when you move it on this circle RBC.
So I gets moved around. Okay, because so as we move I around, you're saying the length RI is constant.
Yeah.
Because it's actually...
You can take 2 points and okay, just take another point on RBC on the bigger arc. It is important that it is on that arc, and draw the perpendicular from U to BC.
Okay. So the distance from here to here is twice the distance from the center to the midpoint, right?
Oh,
so,
yeah, you can also use that. Yeah.
But then we're saying the circle. Oh yeah, because we're moving I around this arc, which is the same as saying we're moving its reflection around this arc. So yeah, that does it too.
Okay, yeah.
Interesting. Okay.
There's actually another way that you can just define point Q and then just prove that it is a fixed point. So you can let the tangents at B and C of circle BIC intersects at a point.
Okay.
It's actually tangent. Yeah, tangent at B and C. Then Q is the midpoint of UJ.
Interesting.
Yeah,
So,
but actually I didn't do it this way back then, but we can prove that the power of point Q, which respect to circle BIC, is equal to QJ squared. And then we just do a little calculating, then we can prove that QJ is constant.
okay. And that Q, you said,
So it's actually like this. Can you unhide point N?
yeah, M,
Point N, unhide point N.
this N. Sorry.
No, the N, like the intersection of MD and BRC.
Okay. Oh, this one. Sorry. All right.
Yeah. So let me see. And intersects NJ with BIC.
Okay.
Then can you unhide point like the Excenter in the original problem?
Yeah.
Yeah.
Should I draw these two?
No, you don't need to.
Okay. Oops. My bad. Sorry. What? I think I need to like click and then I need to do this. There we go. So here's IA. And then I want to show this.
Point G2? Yeah, point G2.
Okay.
Yeah, that's enough.
Okay.
Then
It's
by
like
the butterfly theorem, we can see that NJ and GV are collinear.
okay. Interesting. So we're using the butterfly theorem.
Yeah, so we have angle MJQ is angle MIAV because QJ and VIA are parallel.
Okay.
And it is equal to MNJ.
And
So we have the power of point Q, which respect to BIC is QJ squared. In other words, QJ squared is equal to QK squared minus KB squared.
okay. So
Yeah, and since KB and KB is fixed, so we can easily prove that QJ is also fixed.
interesting. So yeah, we're showing Q has the same power with respect to this circle. Because so the power of Q with respect to this circle, sorry, say it one more time. Was it like QM times QN? Is that how you found the power?
Or you can just understand it like this. We have QJ squared is equal to QM times QN, right?
Right.
So Q has the same power with respect to circle BIC and a circle with point J and radius 0. And those two circles are fixed circle, and K and J are fixed. So Q is a fixed point.
Okay. Interesting. Very cool. I like it. I'm not going to type up the whole thing just because we don't have that much time left, but this is really interesting. All right, let's see if we can do one more problem. I don't think
can we go back to the previous problem? I think I've solved it in the meantime.
This one?
No, the one with the radical axis.
Oh, yes, this one.
Yeah. So
Okay,
I think I've solved it.
all right,
I'm gonna be using inversion.
all right,
So we're gonna find the image of the radical axis. So I'm gonna consider an inversion with power with the center V, and the power is the power of V with respect to ABC.
okay. So, sorry,
It's a negative inversion. Yeah, power. So can you connect AV with circle O?
yes,
Also BV and CV.
okay. With circle O, all right,
Yeah, connect BV and CV with O.
so it'll swap all these points.
So we have the inversion swaps A with L,
Okay,
since VA times VF is the power of V,
mm-hmm.
and it swaps C and N. So it must turn circle VAC into line NL.
Okay, so it turns,
Can you draw the line NL?
yes, just a second. So it turns VAC into line ML.
No, NL.
NL. Okay.
Yeah, because it swaps C and N and swap A and L.
And V goes to the point at infinity. Yeah. So that makes sense.
Yeah. And similarly, we have can you intersect VP with circle O?
Yeah.
Yeah, so similarly, it swaps P with Q, swaps B with M. So circle VBP turns to MQ. So we're gonna intersect MQ and NL.
Okay. Sorry, I'm having a little bit of trouble with GeoGebra today. So MQ and NL.
Yeah, and let that point be R.
Okay.
So that means R is actually the image of when you let the two circle meets at another point other than V, then this inversion swaps that point with R. In other words, we need to prove that RV and E are collinear.
Okay.
Yeah,
So
yeah, it swaps that point. Yeah, S goes to R.
okay. So if we could show
So
R, V, and E are collinear, that would solve it.
yeah, that's my point. So I'm gonna be using pole and polar. So my claim is that AB, ML, and PC are collinear.
A, B, ML, and PC. Okay.
Yeah, it is equivalent to the problem actually. So I'm gonna show it why later.
Okay. All right.
So to do this, we wanna let ML meets AB at a point. Let's call it point yeah, whatever point.
Okay.
T, yeah. And then we're gonna compute the ratio TB over TA.
Okay.
So TB over TA is actually LB over LA times MB over MA. So this is a pretty familiar way to calculate the ratio.
TB over TA, is this Menelaus' theorem or no?
No, it's called I don't know what's it called, but it's a pretty familiar lemma where
Okay.
you can calculate the ratio of any like segment passing through a point and a circle.
Okay.
TB over TA is LB over LA
LB over LA times MB over MA.
times MB over MA.
Okay.
So, and similarly, when you let PC meets AB at T prime, you can calculate T prime B over T prime A is PB over PA times CB over CA. And you can easily show that these two are equal.
Okay. So I'm gonna write that out. I'll just say let AV, BV, and CV meet ABC at points shown. Let AB and ML meet at T prime, or first let MQ and LN meet at R. Let AB and LM meet at T prime. And then we would have T prime B over TA is equal to LB over LA times MB over MA. Is that what you were saying the lemma is?
Yeah, it is.
Okay. And then if we
you know what? I didn't really try it, but an alternative way of proving this may be using involutions.
Okay.
Not strictly DDIT, but there is a theorem about involutions that those three, so A, B, ML, and the CP would concur if there is like an involution at T which swaps. Actually, no, there is an involution which swaps A and B, L and M, and C and P on this circle ABC.
Okay.
And we could probably like project an involution onto line BC, for example, through A, and then we would want to show some inversion, swaps, some things. Just you can continue, but just I want to say that.
Interesting. Okay. So there might be a way using involutions to show they concur. But so I'll say, just to finish writing up Kahn's way, let CP intersect LM at T double prime. Then we get, I'll just say we get a similar expression for T double prime B over T double prime A, which shows T prime equals T double prime equals T, i.e. AB, CP, ML curve. Okay. All right. So
we can also prove that Qn passes through T. I think this isn't really that hard, but I'm gonna let me think for a while here. I don't think it is hard since Q and N are defined through V, P, and C. So maybe we can use polar or something.
Is that Pascal's theorem? So
Oh yeah, I got this. So when you let Qn meets PC at a point T1,
Okay.
so um, we're gonna call D the polar of V with respect to circle O. So when you let Qn and PC meets at T1,
Yeah.
so that means that T1 lies on the polar V. So that it means that T1 is the intersection of line D and PC.
Okay.
But we know that the intersection of line D and PC is actually um, lies on AB because we already proven that AB, ML, and PC is collinear.
Okay. So let Qn meet PC at T1, then
T1 lies on the polar of V,
then
with respect to O.
polar of V, and that also lies on AB, is what you're saying.
Yeah, T1 lies on the polar of V, but we know that T also lies on the polar of V because AB and MF meets at T, and
Polar of V. Okay.
yeah, and you know T and T1 all both lies on PC.
See, so implies T equals T1.
Yeah, since they both lie on PC.
Both lie on PC. Okay. And then
So we claim that R, V, and E both lies on the R, V, and E lies on the polar of T. So
okay.
we complete the proof.
Okay. So claim R, V, and E all lie on the polar of T. Okay.
Yeah, so all left is we gotta use the inversion to prove that E lies on the radical axis, and we're done.
Do we need point S? So S is where the circles intersected, and we showed that. Oh, R is the inverse of F. Okay, actually, never mind. We do need F because the inverse of S is R. That's how we did this. Okay. Keep going. Sorry. Um, so I'll just type what I said before. Consider an inversion about V with radius VA times VF. So it takes BVP to MN. No, it takes BVP to MQ. And AVC to FN. So thus it takes S to R. All right. Okay, so do you remember how to do this part?
Yeah, so it just Brocard theorem. So when you use Brocard for quadrilateral NQML, you have R lies on the polar T, and you keep using it for the other two quadrilaterals. You have V and E also lies on the polar of T.
Okay. So I'll just say this can be proven by using Brocard a couple times.
Yeah, it's no, yeah, it's Brocard.
Yeah. And then
Like
so,
use for NQML, you have R lies on the polar T. You use it for QNPC, you have it lies on the polar V.
okay.
Yeah, and that's how I do it.
By the inversion, S, V, and E are collinear. And that implies that E lies on the radical axis of those two. Radical axis of BVP and ABC. All right, so we are out of time. Thanks a lot for sharing the solution. Inversion is always fun. So we've made it. We got through 100 different live stream geometry sessions. Yeah, thanks again for all these really nice solutions. And for everyone on YouTube, thanks for watching and supporting my channel. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So if you want to join, my email is in the description of my video. So thanks again and have a great day.